Have you ever stopped to wonder what's really going on deep inside your phone or your laptop? Well, we're going to pull back the curtain and take a look at the secret and honestly surprisingly simple language that powers every single thing your computer does. So let's just jump right in with the big question, right? How does a machine that's basically made of silicon and metal actually, well, compute? How does it go from being a box of circuits to running your favorite game or letting you edit a photo? Believe it or not, the entire secret sauce boils down to just two fundamental ideas: moving information from one place to another and then changing it. That's it. At its very heart, a computer is just a machine that is unbelievably good at zipping data around and making tiny, precise little changes to it. Okay, so let's dive into that first part. To understand how information moves, we first need to know, well, where does it live? So let's take a look at the computer's most basic components. The most fundamental place data can be is inside something called a register. Think of it as a tiny, wicked fast little storage spot right inside the processor itself. I love this analogy. If the computer's main memory, its RAM, is the kitchen pantry, then a register is the chef's countertop. It only holds the ingredients you need for the exact step you're working on right now. And just like a good chef has little labeled bowls for everything, these registers have specific jobs. Some are general purpose, but others are total specialists. For instance, the program counter acts like a little bookmark in a cookbook, always pointing to the very next instruction the computer needs to follow. And the instruction register, it holds the command that's happening right this second. It's this level of organization that keeps the whole show running without a hitch.
Okay, so we know where the data is sitting, but how do we tell it where to go? For that, we need a language. But here's the catch. This is not a language for humans. This is a language built for the hardware itself.
That language is called Register Transfer Language, or RTL for short. And it's really important to get this. This isn't a programming language like Python or Java that people write apps in. It's more like a super precise shorthand for describing the most basic action possible, moving a piece of data. We're talking about the absolute ground floor of how a computer thinks. And this right here shows you just how simple it is. This one little line is one of the most fundamental commands in all of computing. R2, back arrow, R1. All it means is copy the contents of register R1 into register R2. The really crucial part here is that the data in R1 doesn't go anywhere. It's a copy-paste, not a cut-paste. A perfect duplicate now exists over in R2. Now, this is where things get really clever. We can add a layer of logic. The first type of transfer we saw is unconditional. It just happens, no questions asked. But a conditional transfer, see that little P out front? That's a control signal. The transfer only happens if that signal P is turned on. This is a massive leap. This simple if-then idea is the microscopic seed from which all complex decision-making in your computer grows. Okay, so we can move data between two registers. That's cool. But a processor has dozens, sometimes hundreds of them. How do you connect them all without creating total and utter chaos? Well, let's talk about the data superhighway. I mean, seriously, just try to picture it. If you had to run a dedicated wire from every single register to every other register, you'd have an impossible rat's nest. It would be a nightmare. There has to be a more elegant solution. And of course, there is. It's called the common bus. And the idea is just brilliant. Instead of a messy point-to-point system, all the registers connect to this one shared pathway. It's literally the data superhighway that all information travels on to get from one place to another. So, how does this highway not become a massive traffic jam? It's all about discipline. Think of it like a one-lane road. Only one register is allowed to send data onto the bus at any single moment. These control signals we talked about act like traffic cops, telling one register, okay, it's your turn to talk. Meanwhile, any of the other registers can be listening and just copy that data off the bus as it goes by. So we've pretty much mastered moving data from place to place, but that's only half the story, right? Now we need to cover the second piece of the puzzle, actually changing that data. We need to look at the computer's fundamental actions. Each one of these tiny little actions is called a microoperation. And we mean micro. It's the smallest, most elementary task the processor can possibly perform. We're not talking run a program. We're talking add two numbers, shift these bits to the left, or clear this register. These are the action verbs of the computer's secret language. And here's the part that I find just incredible. Even though a computer does billions of different things, every single one of those tiny actions can be sorted into just four 4 fundamental categories. That's the whole toolbox.
So what are they? First, register transfer, which we've already covered. That's just moving data around. Then you have arithmetic operations, your basic math like adding and subtracting. Next up are logic operations, which let you manipulate the individual ones and zeros. And finally, shift operations, which just slide all the bits in a register one way or the other. Let's look at a quick example of a logic operation, because it's pretty slick. It's called a mask. The idea is to use one set of bits to change another. Here, the AND operation compares 2 bits in the same position. The result is only a 1 if both of the input bits are 1. Otherwise, it's a 0. So we start with our original data, 1101. We apply the mask, 1100. The first position is 1 and 1, so the result is 1. The second is 1 and 1, so that's a 1. The third is 0 and 0, result is 0, and the fourth is 1 and 0, which is also 0. Our final result is 1100. See what happened? We use the mask to selectively clear the last 2 bits of our original data while keeping the first 2.
All right, we've seen all the individual pieces. We've got the storage spots, the language, the highway, and the actions. Now let's put it all together and see how these simple concepts become the building blocks of, well, everything. So here's the entire flow, all in one go. Data sits in a high-speed register. An instruction written in RTL says what to do next. The bus acts as the highway to move that data where it needs to go. And finally, a micro-operation, like an add or shift, actually does the work and changes the data. That's it. That's the loop that makes everything happen. You have to remember, every single thing your computer does is just a sequence of those 4 steps, repeated over and over and over again at a blinding speed. So the final question is, what happens when you take that simple little loop and you run it billions of times every single second? You get everything. Every video you've ever streamed, every document you've written, every virtual world you've explored in a game, it all comes from combining these microscopic, simple steps at an almost unimaginable speed. That is the true power, and honestly, the beautiful simplicity of the computer's secret language.